Hey there, people. Today we are talking about Section 8.3 volumes. And when we are done, we are going to be able to do cross-sectional volumes and volumes of revolution. So on the next page, we have cross-sectional volumes. So write this down, please. When we're done, we will sketch the solid and a typical cross-section. We'll find the formula for the area of that cross-section, and then we'll find our limits, and we will integrate to find the total volume. So if you need this, pause the video, write it down. So let's say that there is a solid made so its base is the shape of a region between the x-axis and the line y equals 2x. So right here, each cross section cut perpendicular to the x-axis is a square whose side lengths run from the x-axis to y equals 2x. We are finding the volume of that solid on the integral from 0 to 3. So this is the section graph. We're looking at this. That's the base. So if I could lay it flat, I would. That would be the base. And our cross sections are squares that are being cut standing up from the base. Okay, so we need to determine the formula for the area of each cross section. It's a square here, so we have A equals S squared. We need to find the formula for any given side length. So we know that the area of the square obviously is A squared, but what is our side length? Well, our side length here is the distance from top to bottom. Well, the top is 2x and the bottom is 0. And then we are squaring that. So basically we have 4x squared. We are determining the limits of integration. We are obviously going from 0 to 3 because I wrote it down for us. So if there's two curves and they meet at a point, you're going to have to find that point there for us. And then it says integrate the area on the interval. So basically what we're doing from 0 to 3, we are finding each square. We're finding each square's area, cutting all the way through until from 0 until 3. So we are just anti-differentiating this. And plugging our stuff in. So we got 27 times 4 minus 0. There we go. There's our cross-sectional area. The next one, we're going to have very similar stuff. So it says, let's say that we have a different solid now. It's made so its base is the shape of the region between the x-axis and the line y equals 2x. That hasn't changed. Each cross-section cut perpendicular to the x-axis is a square. We have another square here, but its diagonal runs from the x-axis to 2x. So they look like this now. So I'm going back to the last page. We had our squares coming straight out. So this was the side length, but now on ours here, it's the diagonal. So we need to find the volume of the solid. So our section is graphed. I'm just going through those 4 steps. Next, we're determining the area. Again, area of a square is S squared, but we have the diagonal, so we're going to need to work backwards to find the area. So in any square, if we have the diagonal x, its side length then is x divided by square root of 2. That's your 40, 45, 90 triangle. And then to find the area, we are taking x divided by square root of 2 squared. So you get x squared over 2. That's our new area. Our limits, of course, we're going from 0 to 3. I gave that to you. And now we are integrating. So from 0 to 3, x squared over 2 dx, don't forget that. Anti-differentiating from 0 to 3. When I put 3 in there, I need to click my extend. There we go. I get 27/6 minus 1, or sorry, minus 0. And then I get 9/2 for that volume there. So same base, but instead of having squares, I decided let's do semicircles. Okay, so our cross sections are semicircles, and I'm giving you the diameter. So the diameter is the distance here all the way across. So again, we know the area of a semicircle. Ooh, I forgot the 1/2 here. 1/2 pi r squared. And our radius is half of this distance from top to bottom. So 2x minus 0 is our diameter. We need to divide that by 2, put it into this formula. That's our radius now. So this is squared. And then I have my 1/2 pi. So I'm going to do some simplifying here. What do I get? X squared. There we go. And determine our limits. We're again going from 0 to 3. And the final step is anti-differentiate. So I'm going, oops, I need to click that button. Go away, go away. Okay, we'll try this again. So from 0 to 3, 1/2 pi x squared dx. Again, remember that you can bring your constants out to the front. It does make it easier to anti-differentiate. And when I do that, I have x cubed over 3, from 0 to 3. So 27/3, which is, by the way, 9. So 1/2 pi times 9. So there's our final answer. Okay. Find the volume of the solid generated by revolving the region bounded by y equals 2x, y equals x, x equals 1, about the x-axis. So let's draw this picture. So I have a coordinate point here. Let's draw our line in. Looks like this. This is our first one. The other one, again, we have a point of 0. It goes up 1 over 1. This looks like that. And then what was it? X equals 1. Boom. Here we go. And then we are revolving it around the x-axis. So what's going to happen? We are looking at this shaded region right in here, little tiny purple region right there. So we are taking this region and we are revolving it around the x-axis. So it is going to kind of look like a top as it's spinning. So if you look at the region of it, the whole thing, it's going to look like the cross section will look like a circle. So pi r squared. And we are, in fact, going to have 2 radiuses. We have radius 1 goes from here to here. That's the big R. And then I'm subtracting the little r because you're actually going to have this little guy right here. you're going to have that cut out of the center. So I have little r squared. And we are doing that from 0 to 1 dx. Of course, I need to change my big R and little r. We need to find what the big radius is and what the little radius is. So my big radius is that top line minus the axis, so 2x. So I'm going to put 2x in here, square it. I'm going to pull the pi to the front. 0 to 1. And yes, you can simplify to doing this if you want. Move this out. My next one, I am taking x minus 0. So my little r is just going to be the line x minus 0, which is just x. So I am doing x squared in here. If I simplify, put this all in 1, I'm not sure why I split it into 2. Put it back into 1. All right, so I have this. I have 4x squared minus x squared dx. So I'm going to do some simplifying because it's going to actually take less time for me to simplify here and to do my antidifferentiation. So antiderive from 0 to 1. So pi times 1 minus 0, pi. Final volume on that. So we are going to go through these in class. So what I would like you to do is set them up and make sure that you have them so we can do them in class. Okay? So you're finding the volume of the solid generated by revolving the region bounded by, you have x squared in the lines y equals 4 and x equals 0. And we are doing it about the first the x-axis, then the y-axis. So this needs to be in terms of y. This guy here, we're revolving around the line y equals 4, and this is around x equals 4. So this is going to be dy. These over here are dx. Okay, so I suggest drawing a different picture for each. So set those up and at least do the setup, the drawing, and then have it ready to go because we're going to start class with these 4 problems.